kijken of we dat weer hebben. Kijk, zoveel mogelijk geld maken, daarna zou ik vaak geld maken. Dan heb ik even al een jaar niet meer. Kijken of daar zeker als het heeft geschreven is.
Good afternoon, ladies and gentlemen. We now resume our session for this afternoon. During the second half, we have 4 speakers, and the first speaker is Mr. Seamus Darling. Mr. Seamus Darling is the head of engineering for the Commissioners of Ireland Lice, with the responsibility for delivery of engineering, strategy, planning, investment, design, maintenance, all Irish lice-based navigation. He is currently Vice Chairman of the Ireland EEP Committee and member of the Ireland Policy Advisory Panel. He is also a chartered engineer and a fellow of the Institute of Engineering and Technology and a fellow of the Royal Institute of Navigation. Assistant Director for the DGPS of the General Lighthouse Authority of the UK and Ireland. Yes, Seamus, please.
Thank you, Chairman, and good afternoon again, ladies and gentlemen. This is a joint paper, mainly authored by Dr. Alan Grant and Dr. Nick Ward from the General Lighthouse Authority, or an RNAV Directorate, with Alan Cran from the Northern Lighthouse Board in Scotland, Richard Tompkins from Trinity House in the UK, and myself. A summary that you're probably all familiar with. The Navstar GPS system comprises a constellation of 24 satellites in orbit. This provides a nominal accuracy of about 20 meters pretty much worldwide. However, there is a risk if the timing of the signals from the satellites is in error. It can create very serious position errors for users at sea. There is therefore a need for integrity monitoring as well as the more familiar accuracy improvement. If the satellite signals are picked up at a fixed remote site of known position, the instantaneous timing errors for each satellite can be calculated and corrections can be generated. If these corrections are then broadcast and picked up by the user's receivers, the timing errors at the user's receiver can be removed. This is the DGPS, or differential GPS concept. The DGPS system verifies the integrity of the GPS signals. Any satellite signals with small errors are corrected, while alarms are generated for satellites with large errors, so that the user's receiver omit these large errors from the determination of position. The GLAs installed a DGPS system back in 1998. The mission statement was to provide an unencrypted DGPS correction and integrity warning service covering at least the coastal zones up to 50 nautical miles seaward for users with DGPS receivers. Service availability should be 99.8% in areas of overlapping coverage. The system provides a 2D accuracy of better than 5 meters at 95% confidence level. The installed system comprises 14 reference stations distributed over the UK and Ireland. There are 6 far-field integrity monitors, again distributed over the UK and Ireland. Shown here is green. These are used to monitor the long-range performance of the broadcast stations. there are 3 central control stations, marked orange here, 1 in Dublin in Ireland, 1 in Harwich, the east coast of England, and 1 in Edinburgh in Scotland. The 3 control centres are linked together so that they can share information and can act as backup to each other. The broadcast stations are set up such that there is overlapping coverage between stations out to at least 50 nautical miles from the coast in all areas. In this way, if one broadcast station fails, service is still available from the overlapping stations out to 50 nautical miles. This coverage diagram shows the full coverage from the stations in daytime. The ranges of the transmitters are set to ensure that overlapping coverage out to 50 nautical miles all around the coast exists at night time when interference is at its greatest. This is a typical DGPS station. RS1 and 2 are the reference stations in the centre. They pick up signals from the satellites in view and compute the time errors and generate corrections. The corrections are then sent to the right to the transmitter and are broadcast. The broadcast signals are picked up on the integrity monitors, IM1 and 2. On the left, the integrity monitors check that the signal strength is within limits and that the corrections are within the required time and required accuracy. Integrity monitors report to the central station on the extreme left over ADSL communication lines. On the left here is a typical reference station and integrity monitor. On the right is the transmitter. In recent years, support for the reference station has been withdrawn because the equipment is obsolete. On the right, the manufacturer of the transmitter ceased trading. There was therefore a need to re-equip the GLA DGPS network. In order to ensure that we were doing the right thing, we set up a study in conjunction with a consultant to consider options for providing GNSS integrity and accuracy improvement in order to meet the navigational requirements for coastal, port approach and restricted waters as set out in IMO Resolution A915-22 for future GNSS. The study started out with an evaluation of different concepts for providing service. Technical analysis was then carried out on each of the options. The anticipated performance of each option was then evaluated. At this stage, the options under consideration were narrowed down. A risk analysis of the various options was then carried out to evaluate the project risks. An initial cost evaluation was carried out in order to generate a project budget. And the study concluded with recommendations. Looking at this study in somewhat